Hello, everyone. I'm very delighted to meet all of you, and I appreciate you all taking the time out for today's webinar on singularity containers for bioinformatics workflows. As Alex mentioned, I am Tanishta Nandi, and I did my PhD in bioinformatics, and I do scientific computing consulting here at the University of Calgary in Research Computing Services Group. I spend most of my time supporting users on the university's local HPC infrastructure, as well as on the Compute Canada systems. Okay, so I've got 3 goals for today that are really going to get you pointed, I hope, in the right direction so that you can better understand what Singularity Container is about and how you can get started. So first, we are going to look at sort of what an HPC environment looks like, so you can get a better understanding of how the containers fit into this environment. We will look at some of the repositories from where you're able to get pre-built containers. Then I'll also take a few examples of Singularity recipe files to build customized containers. And finally, we'll talk about these containers and how they are used in the HPC cluster through job schedulers. So hopefully we'll get through all of these. So we all work on our personal devices, laptops, workstations, MacBooks, etc., and through which we access the high performance computing systems. For example, the HPC system can be one of the Compute Canada clusters like Cedar, Graham, Beluga, etc., or it can be the university's local HPC cluster. So typically, which means that you are working at your desktop or laptop, and you will be logging into a head node or a login node, which is essentially the landing point into the HPC cluster. And from this login node, you will be submitting jobs to the compute nodes via job scheduler. And all the computing gets done by the compute node. So we are working on a compute node, and that's where we will first review the HPC environment on a compute node. So typically, when we talk of a compute node or a computer, we often talk about CPUs, memory, graphic cards, network adapter, disk drives, and so on, right? These are the hardware components. We also have the operating system. It is the piece of software that can interface with the hardware. So the operating system that we are dealing on a HPC system today is Linux. So this operating system is broken down into 2 parts. First, the user space. So the vast majority of the programs that we are interested in to use, like SAM tools, Cell Ranger, Cufflinks, Top Hat 2, or whatever bioinformatics application or tool that you're using, including the terminal that we work on, they all run in the user space. Now, this user space also includes some libraries. So what are these libraries? A library is a collection of pre-compiled pieces of code that provides functionality to the program the user wants to run. For instance, if you are running a program that needs to perform some math operations, so you don't have to create a new math function for it. You can very well leverage on some of these existing functions in the libraries and use them for your use. For example, you have MKL, which is basically which is Intel's math kernel library. So let's say you are interested in using an application called Cell Ranger or cufflinks. They often have dependencies on one or many of these libraries. And thus, these libraries are needed for the functionality of the application that you are running. Kernel is the other part of the operating system, and that is responsible for the most sensitive tasks, like interfacing with the physical devices, managing resources that are available to the programs, and so on. So, for example, when we launch a program, say SAMtools, the kernel will allocate it the physical memory and provide access to other computing resources, whatever it needs, like CPUs, files, and other devices, and so on. So here is an example. On a HPC system, what happens when we type in a command to do something? There's a program called terminal that reads the input from keyboard and passes that input to another program called shell. Now, both these programs, they run in the user space. Then shell program executes the command, whatever that command is. For example, to list the contents of the root directory, which is the topmost level directory in Linux. The user could write a command called something like this, ls // As the user type in this command, the terminal feeds the input to the shell. Shell executes the command and presents the output on the screen. So the shell is running in a terminal, will take the input interactively from the user. Okay. So you can see the output something like this for a command ls // and it lists all the directories at the root level, which include your home directory where all your user home directories are, opt directory, scratch directory, and many, many other directories as well. Now, the containers that we are going to talk about is just like another program that sits in the user space over here. Containers provide an isolated environment to the program, or if it has multiple programs, to all of those. So containers are able to package one or more programs together with everything that is needed to run those programs. When I say this, I mean it includes libraries, compilers, and other files. They are all collectively referred as dependencies. So the resulting container package is called an image, a container image. They are often saved with an extension .sif or .simg. Now, these images then can be run as containers via programs like Singularity that communicates with the host operating system. Now, these containers can make use of the same kernel as the operating system they run on. And that is a huge advantage because this makes them less resource intensive than any other virtualization options. For example, other virtualization options would include something like spinning up a VM, which takes up much more computing resources than a container. So that's why containers are so popular. And we can access them in the same fashion as we do for any other application. It interacts through the terminal and shell, and you issue the command that's whatever that is, we'll come to that later, to run a container. Okay, now let's spend a few minutes to understand what problem are we solving by using containerized version of any bioinformatics tool. For a long time, there seems to be a reproducibility crisis in the field with all this next generation and big data thing coming in, right? So it's something that's been talked about, and I came across this Nature article that's published in 2016, and it says that more than 70% of the researchers have tried and failed to reproduce other sciences experiments, and more than half have failed to reproduce their own experiments. And I'm sure if you have worked in the lab, or if you do any type of informatics analysis, you can tell if you try to reproduce people's analysis, it's not always super straightforward, right? And this is one of the main reasons why containers are very helpful. So some of the use cases that you can think of is you can reproduce results from a published journal article, or let's say you have developed a pipeline in a test environment. You can very well move it to a production environment without any reproducibility issue. Or it can be simply that you are using, or you have been using a container on one HPC system, for example, Cedar, and then for some reason you want to move over to Beluga, you can just move over the container and get the same results. So you're almost guaranteed to get the same result on different machines. So that is the main advantage of using containers. So for example, let's review the SAM tool versions available on two Compute Canada systems, Cedar and Beluga, right? So we find that the available versions of SAM tools are not identical across these two systems. Now, let's say you are going to test using SAM tools version 1.8 in Cedar, and then going on to run on SAM tools version 1.9 in Beluga, and something weird will happen, right? Or you will rely on the behavior of a certain version of a library, and another one will be installed on the other machine. So problems arise when the supporting software environment is not identical. And containers are a solution to this problem of how to get software run reliably when moved from one computing environment to another. So if our container image biotools.cif, we have a copy on Cedar, and if we transfer it over to Beluga, we can reproduce the same results. And in bioinformatics, the problem gets compounded because we have multiple softwares in a workflow. For example, in order to extract information from raw sequencing data, multi-stage processes, bioinformatics processes are used, right? So there are challenges in reproducing those analysis pipelines, the programs, the versions, the way the installation goes on different HPC systems, and so on. So these things are better handled if we have the containerized version of the application or the entire workflow. Now, at this point, it all sounds good, but the question is how to get a container image for our own research use. Well, the simplest option is to look around in the public repositories for what you need. Maybe you can find a pre-built container image for your requirement. You can look for them in different container registries. Some of them I have listed here, like Singularity, Cloud Library, Docker Hub, biocontainers. We also have GPU containers from NVIDIA and so on. Or your research collaborator can also build a container and pass it to you. So once you have identified a pre-built container image that you want to use, let's say from a registry that includes all the softwares you need, then you can download this image into one of your directories using the Singularity pull command. So here is an example. This Singularity pull command will pull an image of Python version 3.9 into the current directory and name the image as py39.sif. You can give the image a custom name by specifying it just before the registry prefix. So in this case, the image is called py.sif. And here we are using the Docker Hub. So that's the registry prefix here, Docker. The good thing is most Docker container images will convert into the Singularity image format, .sif. That's what I mean, okay? So now, once you do this, you have a copy of the pre-built container image and it's ready to use. But other times, we may want to build a customized container for something specific to our own research work, right? So now we'll see how we can build a customized container for our use. So before I talk about the customization, there are two things to consider here. First is the access to a local machine with elevated privileges, with sudo privileges, where you have admin rights. And it cannot be the HPC system that you are using, because HPC is a shared multi-tenant resource. And there are multiple users using those systems. As it is a shared system, the users do not have any sudo or elevated access. It is a controlled environment, which is often managed by the team of system administrators. So what will you need? Here, you would need a device, either with a Linux OS, where you have these elevated privileges and you can install Singularity on it. Or if you're working on a MacBook or a Windows, you can spin up a virtual machine with a Linux operating system and then install Singularity in that VM. So that's where you will build your custom images. The second thing that you need is the recipe file with the instructions. So this is the file that decides what goes into the container. In a way, it's a definition file. So it has an extension of .def. These files are called Singularity recipe files. And using these files, you are going to build the container. And whatever you need in that container will go into, in some way or the other, in the recipe file. So let's take a look into a recipe file. And we can talk about the various components. So first, we have a header, which tells us the operating system we are going to install in our container. So this bootstrap component tells us that we are going to be using a container from the Docker Hub as the base to build off. And the from section here tells us specifically what container we are going to be using from the Docker Hub. So in this case, it's a CentOS container, right? Now, it's important to note that if you use the keyword latest, as I have used here, and not specify a version, your container will not be reproducible if the latest version changes at some point. Because people will build the containers of an entirely different base if the latest version has changed at that point. So it's best practice to use a specific version number instead of saying it as latest. So the next to header, we have sections. So the first section here is labels. How do we define a section? Every time it will start with a percentage character and it will be followed by the name of that section. And just keep in mind that all sections in a recipe file, they are optional. So what we have here is the first section is labels. It's kind of the metadata. In this case, I have just put in a creator tag saying that it's a container created by Tanishta Nandi, right? And after that, you can put another section like run script that allows to specify a workflow that this container should perform when it's run. In this case, I'll be running a simple echo statement. So that's it. Now we have our first container recipe ready. This is like as simple as your hello world program. That's the first program that you write in any programming language. So with this recipe, we can actually build a container image. So now let's start building the container image. So we can make this container using sudo singularity build. Sudo gives you the elevated privileges because that's what you need to build a container. And then specify the name of the container that you are going to call it. So in this case, I called it container.sif. And then we can specify what we are going to build from. In this case, it will be the recipe file we just wrote in the previous slide. So it will, if you hit enter, it's going to prompt you for your root password. And then it will build the container. Now this process can take somewhere between few minutes to 30 minutes or even longer, depending upon how complex is your definition file and what all things you have put in, right? But once it's done, you should be able to get a image file, whatever you have called it. In this case, it's container.sif. Okay, so now our container image building is done. To exit, now we need to see whether this container is functioning as expected or not. So to see, the most simple way to execute a container file is just by, like any other program, put a ./ which makes them an executable file, and then you say name of the container, and it echoes the command, the statement that we have put inside the container. So this is the most simple container probably that you can build off. So yeah, you have built the first container. So here's another example. Oh, so sorry, I need to talk about this as well. So oftentimes you will be, let's say, using a pre-built container that you have received for someone else. You are given some information about that container. It's always a good idea to verify what's in the container before using it, right? So let's say I pass you this image, container.safe, and say that, oh, well, it's built off a CentOS 8 operating system, and it's going to do this. But how will you verify the information that I have passed you? So let me introduce you to a Singularity command called inspect. So if you use Singularity inspect and the container name, we see that our label is there. That's what we put in the label section, and along with some other labels that were made by default when the container was built. So from here, I can see that I have the information that I have used a base image from a Docker Hub, and it's a CentOS container with a CentOS operating system version 8, right? So now I may want to note what the latest version points to. In this case, it is 8. So it will be important to note this version for its reproducibility in the future. So I may go back and want to update that latest, replace it with number 8, so that in the future, when I build this, maybe when CentOS has moved to a different version, 8.1 or whatever it is, then I could still go back and build my CentOS 8 container. So next, let's move on to another simple example. So how to build a Singularity container for a Python script. So you need two things. Definitely the Python script, which you want to put in the container, and a definition file. Again, let's open the definition, that's a recipe file, to take a look. So we have a header where we have specified to download it again from the Docker registry that will get the base container. And we are building a Python container, and we have now the specific version of Python that we are interested to use. Same as before, I have a label section in our container, and after the label section, we have another new section, %files, okay? This section allows you to copy files into the container. So here, I am copying the Python script into the container to a directory under /opt. Okay. Then we have another section called post. So this is the section of the recipe file that allows to modify and update the container once the base container has already been created. So we have obtained the base container from the Docker Hub, which has Python 3.9. And now we are building on this base container. So in this case, I'll be updating and installing packages here. You can download files from internet. For example, if you think that in the container, you would be requiring some tools like Git, wget, pip, whatever you can think of, or you think that you might need it, this is the place where you are going to have the instructions to install those scripts, all those tools. So this is a section where you will be able to decide what goes into the container, right? And a quick note here, the %file section where the files are copied in should always be copied before the post section, because that should be available during the build and configuration process. And finally, we have our run script section. So this allows to, as I said, to specify your workflow that the container should perform at the runtime, right? So in this case, what we want to do is we want to run this Python script. So we'll put that command here, Python myscript.py. So now with this recipe file, if we build the Python container, it should be the same process as before using sudo singularity build. We should get a we should get a container ready for the Python script that we have. So now that our container image is ready and it is called python.ceph, let's explore the container. We can use a singularity command called shell to get inside the container, where you can see what all files and libraries that are available to you inside the container. So if I run this command, singularity shell and name of my container image, you see that the prompt has changed from $ to singularity. That tells you that you are now inside the container, right? And we know that we have copied the Python script into a directory into a container directory that's called /opt. So let's make sure that the file is copied into the container. So we can use this command, list command, to see what's there under /opt directory, which is a container directory. Okay, so we see that myscript.py exists there. So it confirms that the Python script is there. So basically what I'm trying to say here is that you can use the shell command to explore the contents of the container, right? So let's exit the container shell here. Next, let's say if you want to run a command from the container. So basically use the container, right? So one way to use the container is using the singularity exec command. So in this example, the syntax I have used is singularity exec. Then you will provide the path and name of the container. So in this case, I am in the same directory. So the container image exists in my current directory. So I haven't given the full path, but in case it is in some other directory, you can give the full path to the container image. And then the command to execute. So what we are executing is Python myscript.py. So this will execute the script and do as the script was instructed to do. You can have more than one Python script, and you can choose which script you want to execute at this point. Another option is to use the singularity command run. What singularity run would return will depend on what you have specified in the run script section of the recipe file. So in this case, since in the run script section, we have included this Python myscript.py, I just need to execute a command like this, singularity run, and name of my container image. The run script will execute Python space myscript.py by itself. It is always so you can run your containers either using exec or run, but it is always recommended to use singularity exec to execute a self-defined run script to your application. So you have basically more control of exactly what you are running from the container, because it may contain more than one application or more than one script that you may want to run. Okay.
There was a question in the chat from Matthew. Does updating using apt-get and installing prerequisites affect reproducibility?
So, yeah, that's a good question. Yeah, so if you are you can always be specific to what you are updating. You can specify the versions, and you can so you can freeze that at that point. And this is when you are building it from your definition file. Once you have built the image, then you are not editing it anymore. Then you are just using the pre-built image. So what you define at the time of definition, that's frozen there once you build the image of that definition file. But you can be very specific exactly to that point, that what version you need there. Matthew, does that answer your question?
Yeah, that answers my question.
Okay. Okay. Now, here is another singularity recipe that's slightly more involved. It is for a container that runs SAM tools, right? So we always start by downloading a base image, either from a Docker Hub or a Singularity Hub that has the desired operating system and as many dependencies as possible, right? And so some of the things we have already seen, we have a label section as before, and now here we have a run script section, and I have purposely used the symbol @ here. What it means here, that it will treat the input arguments as a command and execute it. So for example, in this container, I can put more than one application. One is SAM tools, another one can be FastQC, another one can be BWA, and so on. And when I am executing the container at the runtime, I can choose which application I am going to run at this time. So that argument can be passed on. So that's why you can specify, you can use the symbol here. Right, and then you have another section here, that's a new section, %setup, right? In this section, you can make directories inside the container. So when you are making a directory inside the container, you have to be very careful, because you have to do some sort of a referencing that it knows that it's a container file system. And that's what this variable is doing here. When you say singularity_root file system, so that basically specifies a variable and allows it to create a directory within your container, not at the host system. Like, because if you remember at the beginning, we saw that at the very top level under root, you have similar directories as /op, /scratch, /shared, and so on. So you have to be very careful here, otherwise it can mess up with the host system because you are building the recipe file using sudo permissions. So if you're using setup section, be sure that you are referring to the container file system and not the host file system. So in this case, I'm creating 3 directories inside the container: opt, scratch, and shared. And then I have a post section, again, where you could include the softwares, the libraries, whatever you need in this section. We have seen this before, so I've included a bit more things because I will show you in a minute that why we need Git here, or when you are interacting with the container, you might want to use this command, Unix bash command, which, and so on. So whatever you need, this is the place where you need to install all those functionalities. And finally, here you have the environment section that allows you to define the environment variable that will be set at the runtime, not during the build of the container, not at the build time, but at the runtime. That's the difference. Okay, so when we are talking about this bioinformatics workflows, we can always build one application per container, like one container for SAM tools, one container for BWA, and another container for FastQC. But it's also possible to build a single container with 2 or more different types of these applications. Now, to do that, in the recipe file, we can create separate section for each application. Now, these separate sections, all their section names will start with %app something, right? And each app will have their own custom install. So for example, let's say for SAM tools, I have %app run, and this is specifically for SAM tools. This is similar to the run we have run script we have defined earlier, but now this runtime is only for SAM tools, but nothing else. Similarly, we have %app install SAM tools. So here we will bundle all the steps that we do to install the SAM tool application. So if you look at the commands here, it's essentially the same commands that you would run on your, the steps you would run to install SAM tools in your home directory. For example, the first step would be to git clone the repository. So SAM tool has a dependency on htslib, so that needs to be installed first. So I'm git cloning the repository, getting into that directory, and if then update is needed there, then configure, make, install. And similarly, git cloning the SAM tools repo, go to that directory, configure, make, and install. So these are the exact steps which you will do in your home directory, and now you have bundled that under app install SAM tools. So this 2 sections would install SAM tools and execute SAM tools at the runtime when it is called. Now, if you want to build a container with more than one app, so you can introduce more such sections. So you can have app run BWA, and then exec BWA, app install BWA, and have all the steps to install BWA in that section.
Tanisha, can I ask a question?
Sure.
So when you build an image using that, and if you take the container and put it on a HPSC system, for instance, will those tools be really installed on my local machine?
Yes. So the installation and everything that is needed will be in that image. And when you will transfer this image into your HPC system, everything will move together.
But what is left on my machine, on my local machine?
You have your definition file, which is editable on your local machine. But when you build an image and transfer that image to the HPC system, at that point, it becomes read-only, and you cannot edit that any further. So it's frozen. And that's where you get the reproducibility.
Okay, so let's say I have a machine without SAM tools and I'm building this. If I take the image somewhere else, will SAM tools still be on my local machine? Like, is it physically installed on my local machine, SAM tools, when I build a container?
So it will be
put into the image.
Yeah, so it will be installed into the image. You can run that image on your local machine if you want to access SAM tools on your local machine.
Okay. Okay. So okay, thank you.
So with this recipe file, if you again sudo singularity build, you will have an image with SAM tools in it, right? So exactly what the last question was. Now, when you build that image in your local machine, you will generate this image, let's say biotools.sif. This image can then be transferred to one of the HPC systems that you want to work on, say Cedar, right? Now, this container image will contain everything that is needed to run the applications that you have in the container. For example, SAM tools, BWA, FastQC, whatever you have put into that container. And now when you have this image on the Compute Canada system, now it becomes read-only. At this point, you cannot add any more functionality to this container, but you can use the programs or the applications that are there in that container. So just to review the different commands that we have talked so far to use these containers. So a very simple one is a native command, just execute it if you have just one thing that the container does, and whatever is in your run script by default, that gets executed. If you want to explore the container and you want to go in an interactive mode to explore the different directories and its content within the container, use shell. And there are the two other ways to execute the container will be singularity exec and singularity run. So of the two, exec is more preferable. So for example, if I have biotools SIF, which has SAM tools, BWA, and FastQC, I can choose whether I want to run SAM tools at this point or BWA or FastQC. Now we have the image, we are on an HPC system. Now on HPC system, we run everything on a scheduler. The scheduler which we have on our systems is Slurm. And so how do we run these images through a scheduler? So you will be placed into, let's say, Cedar's head node or login node. From there, you can request an interactive session using the Slurm command slloc. Whatever resources you think is appropriate for your run, you can specify, and then you will be placed on a compute node on Cedar. On a Cedar compute node, if you, the first thing is you will load the Singularity module, and then you will run Singularity shell name of your container. What this would do is will place you inside the container, and you can explore the contents of the container. For example, if you want to see what are your options for SAM tools, you can run SAM tools -- help, which will bring up the help manual with all the flags and what they do for you. Like, what is the command? Something like this. And now, once you know your container and you know what tool and what options that you're going to use, you want to run through hundreds of your samples and you want to have a job script for that. So a job script is basically a bash script where you will have all your commands together and you will submit it as a bad job to the scheduler. How does it look like? So it's a bash script. So the first line is basically telling that everything below this line is getting interpreted by bash as a bash command. And then you have your sbatch directives, which are exactly the same things from which you have used in your interactive session using salloc command. So you have account, you have node, the time, memory that you want, and the number of CPUs per task that you want to request, right? So in this case, I've requested 2 CPUs. So once you have requested your compute resources, then you will load the Singularity module and you could run the Singularity exec and the name of your container and the exact command that you want to run. So a few things here. Now, as you see that I have used a flag -b here. Now, what does this do? We have a container and we have talked about copying files into the container. Now we have hundreds of samples and we have a container image. We are not copying these input files into the container, but we want the container to access our input files from a directory wherever they are sitting on the system. So that the container is able to read the files from a particular directory, you have to bind that directory to the container so that it can have access. So that's what this option does. I can bind the path to my input files here, and then I will access it. Then it will be available to the container when it is running the application. Let's say SAM tools here. Now, this is, you guys must be familiar with this, the SAM tool command, but I would like to bring your attention to one thing, which I have used here, that is --. So this is a flag which is available for SAM tools if you want to run it using the multi-core functionality. It tells you the number of threads that you can use to run SAM tools. If you don't specify anything, the default is 1. So now if I want to run my job faster, doing some sort of a parallel processing using 2 CPU cores, then I must say whatever is that integer here. In this case, I have requested 2 CPU cores, and this request should match up with my Slurm resource request. So I have requested 2 CPUs here, and I want to make use of those 2 CPUs. So I have used this parameter here in SAM tool index and said, let it use 2 core functionality for this run. So that's how we make that resource request match to the application, and whatever we request, everything is getting used up and nothing is wasted. And here you can bind more than one path. Like if you have things to be used by the container, they are located in different directories. For example, you might be having a reference genome, you might be having some other files which the container needs. You can bind as many paths you want, just comma separated. Now, once you have this batch script ready, you can submit it to the scheduler using sbatch. And if this is saved into a file called jobscript.sh, you submit that to the cluster and it will be queued and it will get run when it gets the resources as per the, it will be scheduled by the scheduler to run at an appropriate time. Yeah, I think that's all I have. Thank you for your attention, and I am happy to take your questions.
Thank you, Tanista. There were a lot of questions in the past 10 minutes, so I think I'll just scroll up and I'll start with the question from Pranav. The question is, if some programs use optimization of hardware optimization, how do you need to create a special container for the specific HPC system that you're running on, right? So let's say if you want to use AVX 512 or CPU optimization flags on a specific cluster, do you need to create a specially designed container for that?
Yeah, that's a good question. So containers are little specific in a sense, like it has some, so you have to build a container on a specific kernel and a specific those glib libraries, because those needs to match up for them to work on another system. So yeah, so that's a little bit deeper. You need to match up some things for it has to be the same kernel and other things to work it on another machine.
Okay, there was a question from Sean. In your example 2, why don't you need to specify full path to myscript.py when running exec command?
Yeah, that's a good question. Yes, I didn't just get into that because by default, so that's how the containers are designed. So whatever you install, you put it yourself. You always put into that /opt directory. So by default, it gets run. And I know there are examples out there where they put everything under root and you can just run it from the root. You could specify, but in this case, it's auto-detected. But that's something you could do. You could write Python and specify the full path /opt/myscript.py.
Okay, Brian had a comment. Well, it's not really, well, I guess a question, whether anybody had any issues converting Docker images into Singularity containers. So far, no problems, but just wondering about experience from other parties, attendees.
I think most times it works. I don't know if anybody has any other experience so far.
Yeah, I converted, I don't know, half a dozen different Docker containers into Singularity containers. I have not run into any issues, but yeah, it's possible there are some corner cases. Question from Tatiana: can we include a container in the container a script that runs an application from another container?
Wow, that's complicated, but I'm sure. But you can include everything in one definition file, and you have, I guess you can copy that container into this container and do the proper referencing. Then it should work.
Okay, there's a question from Alex, which was partially answered in your slides about mounting a system directory, but I guess the question is slightly more complex. So the question is, how can I mount, for example, a network scratch location within the container that could be accessed by multiple compute nodes that run my job? So when we use the -b flag, does this -b flag make it available to other compute nodes?
Yeah, so when you mount it, you are making it available to the container, and now wherever your container is executing it, it should be able to read from that. But if you are talking more about the MPI jobs, I'm not sure at this point. I have not tested them with the MPI jobs so far.
Yeah, I guess a question of running MPI jobs inside containers is slightly more complex. I remember somebody, I don't have any experience with this myself. I remember somebody commenting on this that it could be done, but you have to be careful about several things. So, all right, there is a question from Sean. Can one move some locally installed software into an image instead of downloading it from another place? So I guess when you're building a container and you have something installed locally, can you move it into a container without having to use apt-get?
So if you have a tarball, you can copy it into the container. But if you're talking about like if you have an executable outside and you can directly copy it, I would think it may or may not work, because it is, when it is compiled, it has some dependencies and some libraries with it. So you have to weigh that out.
Right. Question from Max: any issues, gotchas when debugging HPC apps wrapped inside Singularity containers? Sorry, say that again. I missed that. Any issues, gotchas when debugging HPC apps inside Singularity containers? So for example, if you run into issues, how would you debug? You're running an application inside a container and you run into problems. How would you debug it? So one thing is, first you run the inspect, and that will tell you what is in the container. Now, if you have access to the recipe file, you can edit it on your local machine where you have more like editable options. You can go back right into that definition file, rebuild the container by fixing whatever you want to. But if you are working with the image, I guess the options are limited there. Another question which I don't really understand: can you access the output of SAM tools on your local machine? So I guess the question is, you do it via terminal, but I'm not sure if you can comment more on this. Yeah, so the thing is, I guess you're asking that when you are running it from running the container, where does the output file goes, right? So if that's the question, you could direct it to the same depends what directory your container has access to. So let's say the local HPC cluster that we have at University of Calgary that mounts the home directory by default. So anything, if you direct it to a subdirectory in your home directory, the files will be written there. Or you could direct your SAM tools output to the directory that you have bound with -b, where you have input files. You create a subdirectory there and direct your output to that directory. Okay. So anywhere the container has access to, you can direct your output there. There's a question from Zohaib. Can you build a Singularity container on CEDAR from a recipe, for example, inside SnakeMake Nextflow workflow? Okay, so on CEDAR, it is, that's what I said in the talk, that CEDAR is an HPC system. It's a shared resource. And there you don't have sudo privileges. So you have to build a container from a recipe file on a system, on a Linux system where you have sudo privileges. It could be a virtual machine with Linux OS. Another question, if you use some proprietary or commercial components inside an image, licensing may prohibit sharing such images. How do you suggest researchers handle such situations? So if it is license dependent, then the license files should be included in the container. Like copy the license.dat so that it is accessible to the software. And I guess in this case, you just modify permissions so that nobody else can access the container, right? So you can make sure that the file is not readable to everybody, to all other users. Yeah, that's right. And last question, can we convert a Singularity container to a Docker container to use on a local machine? Wow, that's a good question. Honestly, I haven't tried. I don't know, Alex, if you have tried that. I have not, no.